let us discuss the problem shortest unique prefix for every word. Previously, this problem has been asked in Microsoft and Google. So the problem says that we'll be given an array of words. So basically, we'll be given some words in an array, and we have to find all the shortest unique prefix to represent each and every word inside the array. And we can assume that no word is a prefix of another. So let us try and see the sample test case. So suppose if we have been given the sample test case like this, let's check this out. So suppose if the sample test case is like we have been given the array of strings where we have been given zebra as one of the strings, another string is dog, then another string is duck, then another string let's say is dove. Okay, if these strings are given to us, so in that case what we can see is we can represent z, the shortest prefix with which we can represent z, like zebra is with z because z is not common with any other guy. Can I represent this dog with d? No, I cannot represent this dog with d because if I represent it with d, so d, like d can also represent duck and dove. Okay, so d is contained in a lot of character in a lot of words, so I cannot represent it with d. Can I represent dog with do? No, I cannot represent it with do as well because if I see, so do will also be common in dove, so that will not be the shortest unique prefix with which I can represent it. Then I can represent it with dog because it is not the same with anyone. Then with this duck, if I see, so can I represent it with d? No, because dog, duck and dove all have d, so d is not the shortest prefix. Then can I represent it with u, du? Yes, I can represent it with du because there is no other word that is containing du as the starting prefix. Then can I represent d with dove, d for dove? No, it's not the prefix with which I can represent dove. Can I represent it with do? No, because dog is also having do. Then can I represent it with dov? Yes. So the final answer is that for z I can represent it with z, like zebra I can represent it with z, dog I can represent it with dog, and duck I can represent it with du, and dove I can represent it with dov. So basically if we'll think in the brute force manner, so this could take a lot of time. And like what you can maybe think of is you will try every prefix, like for zebra you will try with z, then maybe zeb. If you will try with the shortest prefix possible, and then what you will check is that whether or not that prefix is same in each and every word, and you will try it for each, like for all the combinations. Let's say d is this, and then d, you check it for d, then you check it for do, then you check it for dog. So you check d with every word whether it is same or not. If it is same, then you check it for do, then you check it with dog. So that will take a lot of time. Okay, so what we can do here is instead of doing that, we can simply use our trie data structure in this case, and a trie data structure would help us to optimize the implementation of this particular problem. So what does a trie data structure do? So in a trie data structure, like if we have a node, like normally we have a node, and like let's talk about tree. So like our trie data structure is kind of an array tree, we can say. But basically if we talk about a normal tree, so it has a left child, okay, it has a left child and it has a right child. But in terms of tries, it does not have just 2 children, it has 26 children when I talk about a trie that is containing strings. Like, so in that case, if we have a trie, suppose this is one of the nodes, so in that case this particular node will have the information, will have 26 different nodes, right? It will have 26 different nodes, either they can be filled or either they can be empty as well. So it will contain 26 different nodes indicating about 26 different characters, and 0th index will indicate me about a, for like if it is null, or like suppose if a is existing, then it will not be null. Otherwise if b is not existing, suppose, so it will be null, b will be marked as null. Okay, 1 will represent b, 2 will represent c, and similarly 25 will represent z. How? So let's say if there is a character a, if I do a minus a, then I'll get a 0. That will be enough to represent a. If I do b minus a, then I'll be able to represent 1. If I do c minus if I do c minus a, then I'll be getting 2, which will be able to represent c. Then what I do is if I do d minus d minus a, then I'll get 3, which will represent d. Then I do z minus a, which will give me 25, so 25 will represent z. So that is how I'm going to represent. And every trie, I'll make a class of trie, and what I will do is every node will not only contain the information about the 26 pointers, It will not only have the 26 children that it can have, it will also contain the information about the frequency. So it will also have a frequency variable with it. Okay. And what we will do is, first of all, we'll start with the root node. So we'll first of all do what? We'll make a root node of the trie data structure that we are wanting to implement. So let us say that if we make the root node, okay, first of all we'll make the root node, and then what we'll do is we'll start the inserting process. Okay, so we'll start the insertion process for each and every word present in the array that has been given to us. So when we have zebra, so what we will do is, first of all, I'll start. So I start from z. So is the root, if I'm currently starting from the root of the given trie, so does it have a z? No, currently z is null. So that means I'll make a node z. Okay, for z I'll make a node. Then I go to e. So is there a e existing? From, if I'll be currently at z, so like I'll mark the frequency count as 1. So for z I'll mark the counter as 1. Okay, I'll mark the frequency count as 1 for z, and then I move to e. So is there e existing for z? No. So I'll make a e for myself, and I'll mark the counter as 1 here as well. Then what I will do is I'll move to b. So is there a b existing for e? No. So I'll mark a b here. Then I move to r. So is there a r existing for b? No. So I'll make a r. Then I move to a. So is there a existing for r? No. So I'll make it, and then, so this will be, counter will be marked as 1 here, counter will be marked as 1 here, counter will be marked as 1 here. Okay, we'll see how the counter would be helping us later on. Then what we'll do is, if I come to this word dog, so from the root, if I start again, so is there a d existing? No. So I'll make a d first of all, and then what I will do is I'll mark the counter as 1. Fine. Then what will happen? I'll move to o. So is there o existing for d? No, it does not have any o. So I'll say that, okay, let's insert an o. Then I'll have g. So first of all I'll mark the counter as 1, then I'll move to g. So o, for o there is no g existing, so I'll make a g as well, and I'll make its count as 1 as well. Then what happens? I'll insert this word duck. So the moment I move to this duck, so do I have a g? Yes, I do have a, like, do I have a d? Yes, the root does have a d. So now I can say that I'll simply traverse this part. So from root I'll move to d. Then does this d have a u? No. So I'll insert this u. Okay. Then does this u have a c? No. So I'll make a c. But before that, if we have moved to d, so we have moved to d again. So that's why its frequency will increase. And now the frequency of d would increase to 2, because we have moved it 2 times. Move to it 2 times. Then the counter 1 for u is 1, and then c. So c, for c the counter is 1 as well. Okay. Then I'll write it somewhere here. Like the counter is 1 here for u, and for c also the counter is 1. Then what will happen? I will insert k, because k is not present, so I'll insert k as well, and I'll mark the count as 1. Okay. After this part, I'll insert the next word. So the next word is dove. Do I have a d for the root? Yes. So I have a d, so that means I'll traverse it and I'll increase its frequency. Now d's frequency changes to 3. Now do I have a o? Yes, I also have a o. After d I have a o, so that means o is having frequency 1. Now it will increase and it will change to 2. Then what will happen? I have a v. So do I have a v for this o? No. So I'll insert a v here, right? And I'll mark the count as 1. Then do I have, for this v, do I have e? No. So I'll insert it and I'll mark the count as 1. Okay, that is what we will do. And then once we have built this trie, let me make this here. Okay, so basically this is how we are making it, like this, do and then ve. Okay, that is how we have made it. Now what I will do is, after the trie insert operation has been made, after the trie has been built for the given words, then I'll iterate through each and every word one by one. So once I'm at zebra, okay, so for zebra, can I say that I can, I'll try to represent it with the z. So can I represent it with z? If I move from the root, if I move to z, so the count is 1. So that means no other word is having this z, right? That is why the frequency is 1. So that's why I'll say that, okay, I can represent zebra with z. So I'll say that, okay, let's represent zebra with z, and then I will move to the next word, because zebra can be represented with the shortest prefix, shortest unique prefix will be z. Then if I move to dog, so what happens with dog? If I represent it with d, so if I move to d, so d is having what? D is having the frequency as nothing but 3. So that means d is not unique to this word dog. D is contained in 3 other words. So then what I'll do is I'll move down. So if I move to o, o is contained by 2 words, because it is contained in dove and o as well, dog as well. So that will not be possible for me as well to represent it with do. So now I'll move again. I'll move down and I see that G is represented by G is contained in just one word because it is having the frequency as 1. So the moment it has a particular node has the frequency 1, so I can say that okay, I can represent it. And I'll say that okay, I can represent it with D, O and G. So I'll say that I can represent dog with DOG. So zebra with, I can represent zebra with Z and dog with DOG. Then the next word will be duck. So I'll start for the duck word as well. So I'll start from D. So can I represent duck with D? No, because the frequency of D is what in this try? The frequency of D is nothing but 3. So I cannot. Then I move to U. So can I represent it with DU? Yes, because U is having frequency as 1. So U is not common to any other word. So that's why I can represent it with DU, and I'll say that okay, we can represent duck with nothing but DU here. Okay. Then I come to this word DOVE. When I come to this word DOVE, then again I'll traverse through the try. So I move to D. So D cannot represent dove because D is contained in 3 words. D is not having the frequency as 1. Then I move to O. O is also having frequency as 2. So that means I cannot represent it uniquely. So DO cannot represent. Then I move to V. The moment I move to V, so V is having the frequency as 1 because V has been traversed only once. So that means DOV is unique to dove, and dove can be represented with DOV. That is what we will do. And then we can simply return this answer that we have stored, like Z for zebra, dog will be represented by DOG, and duck will be represented by DU, and dove will be represented by DOV. Okay, that is what we will do. Let us try and see the code for this particular program. So I have written it already so that we can focus more on the implementation part and how we are implementing it. So we have like first of all what I've done is I've made a try node, okay, and it will consist of 26 like every try node will consist of 26 characters. Okay, I've made the count as well, and what I've done is for every node I've initially marked as initially initialized it with null, and I've marked the counter as 0. That is what we have done with the try basically. And then what we have done is in this find prefix function in which we have been given the rf strings and the n strings that are there. And first of all I'll make the try root of the try. I'll first of all make the root node, and then I'll perform the insert operation for each and every ith word. Starting from the root, I'll perform the insert operation for each and every word. So what I'll be doing in the insert operation is I'll simply check that if the root contains the ith word, I'll iterate through the words one by one of the given string s of the current string that I am at, of the current word that I am at, and if that particular word is equal to null, if it is not inserted, right? So in that case I'll insert it, and then I'll say that okay, root should point to that node. So first of all I'll make it, and then I'll point my root to I'll point my current node to it. Okay, and then otherwise if it is already present, then I'll move to it. Otherwise I'll move to it. So I'll update my root. I'll move throughout the try one by one down. Okay, that is what I'll doing. And if I'll keep on increasing the current root that I'm at, I'll keep on increasing its frequency one by one, indicating that there is one character, the frequency is 2, indicates that 2 times I've traversed that particular node. Okay, that is what we will do as we talk about the frequency part. Then after this, after we have performed the insert operation in the try, so I'll have an answer that will consist a vector string answer that will contain the answer. So I'll traverse again for each and every word, and I'll initially say that okay, if this ith word I am at, so initially I'll be starting for the ith word from the root, and I'll check. I'll keep on moving my current one by one throughout the try, and the moment it happens that for a particular node in the given word, if the particular node if the particular node of the try for the jth word, if it is equal to 1, if it is having frequency as 1 only, so that means it is unique, and that much part of the substring I will extract from 0. Or you can also do str is equal to s plus is equal to s of j. That is also we can do, or we can directly take out the substring. Both are fine, and then we'll simply break because we have stored the answer for the ith string. Then we will move to the next string, the I plus 1th string, so that we can try to store the shortest unique prefix for it as well. Once we have stored it, so we'll simply return the answer. So that is what we have done in this particular program. And talking about the time complexity of this approach, so since there are total n number of words, so the time complexity will be nothing but n into the length of each word, because what I am doing is I am iterating through each, if I am iterating through one word, so one word is taking order of length of each word, like order of length of the word time to build a try. Okay, That is what we are doing, and that is what we are doing in iteration as well. But since there are n words, so it will take n into length of each word, and the space complexity will also be n into length of each word, because I am storing it inside the trie. So this was it for this video. Thank you. In this video, we will discuss the problem word break using trie. The problem previously has been asked in a lot of product based companies like Google and others. The problem says that we'll be given a string A, and we'll also be given a dictionary of n words, that is B, and we have to find out if A can be segmented into space separated sequences of the dictionary word. So let us try and see what the problem actually says. So if we take a look at the sample example that has been given to us, so let's say the sample example has been given, and in the sample example, suppose we have been given I, then we have been given the strings like, we have been given, let's say, Sam also. Suppose we have been given Samsung as well, and suppose we have been given SUNG as well. Then we have been given, let's say, man. Let's say we have been given go, and we have been given mango as well. So if these are the strings, suppose that we have been given, although there are more. So let's say we have been given ice, and then ice cream as well. Okay, then we have been given cream here as well. So suppose these words have been given for us. So what we need to do is we'll be given A. So what is A here? A is I like, but it is together. Okay, it is together. I like is not different, like it does not have spaces in between. It is like I, then without a space we have like. So what we have to do is we have to find that whether we can segment this I like, and like this complete word is like. What we have to do is we have to check that whether we can make some spaces, whether we can segment it into words such that those words are present inside this particular uh, dictionary that has been given to us. So that is what our task is. So we can observe that if we do I, then we segment, we make a segment, we make a space. Like we basically do what when we have been given I like. So we break the string from here, and then we try and check whether I and like are present or not. So if I check I and like as well, so if I search that okay I is present or not, so yes I is present, perfect. So then we'll check okay is like present or not, so like is also present. Then we will say that okay it is possible to make I like in some combination or the other, and we'll say that okay we'll print a yes. Suppose we have been given some string like Samsung, and in this case if we have been given Samsung, suppose Samsung was not given as the answer finally. So in this case if we have been given Samsung, so what we can do is we can break it from here, right? We can break it up to this M. So we can make it like Sam and Sung, and then we can try to search whether, like, first of all we'll search Sam is present or not. So we can see that okay Sam is present, we can see Sam is present, then Sung is present or not, Sung is also present. So in this case also we'll return a true that okay it can be segmented, right? It can be segmented. So that is what we will do. Like if I move down to the second test case, like if we see this case where we have been given I like Samsung, together we have been given this thing. Okay, so suppose we have been given a word like, first of all let me write Samsung as well. So what we have been given here is like suppose we have been given I, like suppose we have been given A, which is like I like without any space. These all the characters are given I like, then Sam, and then Sung. Okay, if these words are given to us, so what we can do is we can make one segment here. So I, and then I can search for like, and then Sam, Sung. So is it present? No. So I'll not, basically I'll not get disheartened, and what we will do is like there's one space. So what we'll do is we'll now try to fragment this up. Okay, we search like segment like and Samsung is not present, this word is not present. So we'll make segments. So we'll make segment with L, then like we'll try possible segments, but then we'll search that like, and then Samsung is present or not. So to our surprise, like I is also present, like is present, and Samsung is present. So that's why we'll return a true. But suppose if Samsung was not present, in that case, what, like, should we return a false? No, because in that case, like Samsung, when we break it like this, then we'll search for this as well. We'll basically, you can understand that if you are doing something again and again here, breaking again and again, like having some segment, then breaking it from here, then having this segment and breaking it. So that what we are trying to do is we are basically trying to use recursion here. When we have this Samsung here, so we'll break it from here and we'll write it as Sam and Sung, and then we'll search whether these words are present. Yes, Sam is present, Sung is present. I was present already, like was present already. So I like Sam and then Sung. So in that case, it is present. So that's why we'll return a true, otherwise we'll return a false. So for doing this thing, what we can basically do is we can try and use the try data structure. We can implement this problem with the help of try data structure, although there can be other approach as well. But this problem says that, if you will observe, it says that we have to use it, we have to solve it using try data structure. So what can we do now? So we will first of all learn like how we can use the try data structure here. So like actually what try does. So a try data structure is like, if we talk about tree. So a tree, if we talk about tree, so tree has a left child, okay, and a tree has a right child. But like in case of a try, it is like an array tree, we can say. Basically a try is what? A try is having nodes, and it has the information. If we are making it of strings, so it has information about all the 26 characters. So it can go in 26 directions, although it can be null as well. So what, like it will, like basically it will indicate for a b c d, for from a particular node it will indicate like this. Okay, so what we do with the try data structure is, we first of all will make the words that have been given to us, and then we'll try to search. So try does what? Try makes our search process for the words easy. It makes faster retrieval of words. It helps us to search the words easily. It is also used in autocomplete features, like we can see in Google's search bar. Whenever we search a word, we are recommended some words, some words, let's say we have search, let's say we suggest, like we search geek, then it suggests us geeks for geeks. So that is done using the try data structure. Okay, so now what we will do is, first of all we'll see like how we actually implement it. So like let's just suppose that we have been given some of the words here. Suppose we have been given some words, like we have been given Sam, suppose we have been given Sung, suppose we have been given Samsung as well. So first of all we'll see how we can write these words, right? Okay, like, and suppose we have been given some other word, like we have been given like study, we have been given a word as a study as well. So what we will do here is, we will have the root node of the try. Okay, and from the root node we'll check. So is the, if from the root node, is the, like suppose I'm inserting s, Sam. So in that case, is there a s present? No. So that's why I'll say that, okay, let's mark our s and then move our pointer to this node. Okay, then what we'll do is, from this, is an a present? No. So I'll say that, okay, let's mark our a as well. And then what we'll try to do is, we will try to again search whether m is present or not. So m is not present for a, so I'll write m as well. Then what we will do is, we'll try to insert Sung. So when we start from the root again, so is there a s present? Yes. So is there a u present for from s? No. So I'll insert a u. Okay, here I will indicate that, okay, this word has ended. Then u is there. Then n, okay, and then g. Then I'll indicate that, okay, this word ends here. Then I have a Samsung. So if you give me a Samsung, so I can say that, okay, this word is ending here, so I can indicate it like this, something like this. Okay, I can use a variable like true, false or something. I can implement it in various ways. Now what I will do is, if I have Samsung, so if I have Sam, so I'll go down, I'll see, okay, s is present, a is present, m is present. Then I'll insert Sung, so s, then u, then n, and then g. So and then I'll indicate that, okay, this word is ending. So I've inserted Samsung as well. After that, what we'll do is, we'll insert I. So from this root I'll start. So is there any I present? No. So I'll say that, okay, let's insert an I. After this I'll insert like. So L is not present, so first of all L. Then for this L, no I is present, so I'll have I. Then for this I, no K is present, so K. Then E. Okay, after this is study. So for this, if I have to write study here, so S is present, right? If I move down, so from the root S is present, then T. For T, U is not present, so I'll insert it U. Then D, then Y. And now if I have to search for some words, so try makes the searching easier for me, because if I have to search, let's say a word like Sung, so I'll move to S, then I'll move to U, then I move to N, then I move to G. Suppose if I had to search for the word, okay, or let's say I had to search some word like sat. So if I have to search for it, I'll move down, I'll move to A. So S and A are present. Is there any T present for A? No. So that case I'll return a false, that, okay, this word is not present. So that is what we will be doing here, and we'll be dividing efficiently. From every index we'll try to divide such that we can find it. So we'll write functions for that. The functions will be recursive in nature, because we'll be doing this task again and again. let us try and see the code implementation for this particular approach. So what we'll be doing is, first of all, we'll have this like size will be declared as 26 because every node will have 26 children for it. Okay, and we'll also have a variable bool is end of word in the try, that will indicate that it will indicate true, that means that the word has ended here. If it indicates false, that means that the word is not ending here. And then what we'll do is like we'll also have, like suppose we have this particular function word break. So in this, first of all, we'll be given the word a. So first of all, we'll declare the root node, and then what we'll do is we'll simply implement the insert function. So we'll insert each and every word that has been given inside the try. Let us see how. So what we will be doing there is like we will be simply iterating, and initially we have marked all the children as null and the word as false. Then what we will do is we'll have the insert function, and inside the insert function what we will be doing is we'll say that we want to insert this particular word that is there. So we'll make mark our current variable to the root. Okay, then we'll iterate through each and every character of the word one by one, and if that character is not present inside the try, then we will basically make a new node and insert it. Otherwise we will directly move to the that node that is present. And in the end, after the word has ended, so for that particular node at which the word ends, I'll mark it as true. So that is how I'm performing the insert operation. Then there is a search operation inside the try as well. You can understand why I'll be having the search operation. Basically, if a particular string is there, one by one, if I'll keep on segmenting the words that is given in A, so if I segment them up, so what I will try to do is I'll try to search them. So basically for searching, I'll initially point to the root, and then I'll try to search that like for every ith character, I'll try to search whether that character is present or not. If a particular character that I'm searching for, if it is not present, immediately I'll return a true. Otherwise, if it is present, then I'll move my pointer to that particular node. And what I need to do is I need to check that if my root is not, if currently I'm not pointing to null and I reach the end of the word, in that case I'll simply return a true. So that is what we are doing, and this is the break function that we have made. This is the recursive function in which we'll be doing the segmentation of the word A that has been given to us. So we'll segment it one by one recursively. So what we will do is if the size is 0, we simply return 0, a true. Otherwise we'll try to segment it from the index size equal to 1 until the size, okay, of the word, that is like until the size. And what we will try to do is we'll try to like first of all we'll try to search, like we will try to make a substring from 0 to I, and we'll try to find whether from 0 to I that particular substring is present or not. If that particular substring is present inside the try, so that means it is present in my dictionary and I can make it. And then I will also search that for the rest of the word. So I'll try to make this again, this recursive function I'll try to make from I till size minus 1. Like I'll tell you here, like basically what will happen if I is there, like if suppose that Sam is there, right? If Sam is there and Sung is there, so first of all what I'll try to do is I'll try to make S, right, and then AMSUNG. Okay, then I'll try to search for every possible combination, right? S, then A, then M, like every possible combination that I can search for, I'll try to search for. And then like while I'm breaking, so once what will happen, Sam will be searched and Sung will be searched, both will be existing. So that's why I'll return a true in that case, because they will be existing inside the try. In that case, if they're existing, so I'll return a true, otherwise I'll return a false. So that is how we are implementing this particular approach using the try data structure, and this problem is pretty important. So thank you for watching this video.